One very broad way of classifying solids is to classify them as crystalline or amorphous solids. And basically what that means is they either crystallize or they don't. The crystalline structures, there are a few different ones. Here are some common examples. This one is body-centered cubic, and I guess there are four examples here really. The most simple example would be something like table salt, where there would be one in each corner and nothing in the middle. Then from there, cubic body-centered, where it would be like table salt, where everything would be in one corner, but there is an additional one in the middle. And then there's cubic face-centered, where imagine a cube, and in the middle of the face of each cube is another atom or molecule, whatever it may be. And then there's this hexagonal one, which I don't really know that much about, so I'm not going to say anything about it. I don't know anything about it. Never really dealt with it before. But a lot of people, well, they're just good to know how solids work, just on a very basic level, what's going on, because a lot of people assume more stuff is amorphous than it is. Most people can look at water or salt, things like that, different crystals, and it's obviously crystallized. But things like gold, silver, nickel, copper, people don't generally think of that as crystallized. It just looks like a lumpy ball, and people would probably think that was amorphous, but it's actually a crystalline structure. And one other interesting thing that people can do with these, if I know how, let's take for example, let's use gold. So I know that gold is in cubic face-centered arrangement. I can calculate the density from that, because I can essentially use, if I know the atomic radius, of course. If I know the atomic radius, I can then just use Pythagorean theorem, add up these radii, use Pythagorean theorem, and then I know what the mass is from the periodic table, and then I can just calculate the density. So that's one thing that this book likes to do, is calculate densities. But this is just an interesting, I guess, very basic introduction into solids, because it doesn't really go into much detail. But I've seen other books where it continues on, and this is very important for manufacturing of metals and things like that. As something like this, or I think it's here's iron. Something like this, a lot of alloys and stuff are important, and what's important about them is the amount of space that'll be in between the circles if they were to fill up, because something like steel is iron, but then in between the little grooves where there would be space between these, it's kind of hard to tell here, but in between the grooves I'll put carbon or something else. It just depends on the alloy, and depending on how much carbon is in there, they can make different kinds of steel that's more malleable, steel that's hard, like medium hardness, and steel that's extremely tough. It just depends on how much carbon they put in there, or any other type of alloy for that matter. But that's another interesting field of study that this would have a lot more relevance with, which I know absolutely hardly anything about.